students, welcome to physics class. My name is Priscilla Benoba, and I'll be taking you on the topic work in the theme conservation principles. Before we start the class, let's take a look at the objectives. By the end of the lesson, you should be able to explain work and give examples, calculate the work done, given a force and displacement it produces in its direction, explain work in a force field, differentiate the sign or nature of work. Now let's start the class proper. The term work is a concept used by different people. People have different concepts of work. A farmer clearing weeds on his field may be seen as doing work. A woman carrying water from the well may also be doing work. You going to school, doing your homework, some people see it as work. But in physics, we have a specific definition of work. What is work? Work is said to be done whenever a force is applied to displace or move a body through a certain distance in the direction of the force. Now, from this definition, we can see three conditions for us to say work has been done. Number one condition is that the force must be applied. The second one is that the force applied must displace or move a body through a certain distance. And the third condition, that distance must be in the direction of the force. So we can say work is said to be done when an applied force moves or displaces a body in a direction of the force. Now, when we talk about displacement, because we'll be using the term displacement a lot, displacement, as we all know, is a vector quantity in the sense that it has magnitude and direction. So the displacement I'll be using today has magnitude and direction. We can see from this picture that this man is applying a force to move this device, and this device is moved in the direction of the applied force. This man is also pulling a device, and he's doing that in the direction of the force. What are the examples of work done? Work is said to be done when you push a car a certain distance, you lift a load from the floor to a table, you push a box up a frictionless slope, you stretch or compress an elastic body through some distance, and so on. You can see that when you move a car a certain distance, you are applying force in the direction of the force. So the body is said to be displaced when the force is applied. As you can see from this picture, this man is applying a force, and this force that is applied is in the direction of the displacement. So as the car is being displaced, the force is applied. You can see this man here lifting a load. As he lifts this load from the ground, he's doing work. So it means that the distance covered from the ground level where he lifted the load to this height, he has done work. So work is said to be done. And this man moving a box up a frictionless slope, he's applying force, and the box is being displaced. Measurement of work. If a force moves a body at a displacement s in the direction of the force, the work done is given by work is equal to F times S. This F here represents the force, and the S here represents the displacement. So it means when you multiply the force and the displacement, you have work done. So you can define work done as the product of the force and the displacement. Now, work is a scalar quantity. You may have noticed that we are multiplying force and displacement, but these two quantities are vector quantities. How then is the product a scalar quantity? You must know also that the dot product of any two vector quantity gives you a scalar quantity. So the dot product of force, which is a vector quantity, and displacement, which is also a vector quantity, gives you a scalar quantity. And that is why work is a scalar quantity. You can see from the diagram we have, this is the initial position of the body. As force is applied, it is displaced to a final position, and the distance between A and B is the displacement S. And we can also say, so when you apply force, it must be in the direction of the displacement. Then you can say work is done. Also, there is another way you can measure force when it is at an angle, when the force is at an angle to the displacement. Let a constant force F be applied on a body such that it makes an angle theta with the horizontal, and the body moves through a displacement S. Now, when you apply force to a body at an angle theta to the displacement, work is done. And this is the formula for work. It becomes F, which is force, times the displacement times cos theta. Now, you must have known how to resolve force into two components. When you have a force like this, you have two components. You have the y-axis and you have the x-axis. To resolve force in the y-axis, you have F sine theta. So to resolve the force along the x-axis, you have F cos theta. Now, since we are concerned about the horizontal direction, that with the horizontal, you take the x-axis, which is F cos theta. So now your F becomes F cos theta. So when you impute it into the equation of W is equal to F times S, that is work done is equal to F times X. But this your F now is no longer F because it is at an angle theta. But after resolving, you have F is equal to F cos theta. So substituting F cos theta into this equation of work done equal to force times distance or displacement, you have F times S times cos theta, which is now your work done. Now, units of measurement for work. The SI unit, like you know, the International System of Units, which is the one that we mostly use. The SI unit of work is joule. When the force is measured in Newton and the displacement in meters. And 1 Newton meter is equal to 1 joule. You must know this relationship that 1 Newton meter is equal to 1 joule. So when you're giving a force in Newton and you're giving the displacement in meters, your answer will be in joules. And remember, there are various systems of units. We have the CGS system, which is the centimeter, gram, second unit, and we have the foot, pound, second units. Now, remember, these are the various systems of units, the CGS, the FPS, and the SI units. Now, in force, we also have different units for these various systems. We have the Newton, we have the dyne, we have the pound. The Newton is for the SI units, the dyne is for the CGS, which is the centimeter, gram, second unit, and the pound is for the FPS, which is the foot, pound, second unit. And the distance also, we have the meters, the centimeter, and the foot. So work in the SI unit is measured in joule, while in the CGS unit, it is egg, and in the FPS unit, it's the foot, pound unit. So we should take note of these various units. Now, let's look at an example. 100 Newton force was applied to move an object. Calculate the work done if the object was displaced at a horizontal distance of 5 meters. Now, the data given from this question, we have force, which is 100 Newton. We have displacement, which is 5 Newton. Then the work done, which is force times displacement, is simply 100 Newton times 5 meters, which is 500 joules. Isn't that simple? The second example, a box of 50.0 kilogram was dragged along a horizontal plane at an angle of 30 degrees over a distance of 5 meters by a force of 1.20 times 10 raised to power 2 Newton. Calculate the work done. Now we can see from our question that from the data given, we have mass of 50 kilogram angle of 30 degrees, displacement 5 meters, force is 1.20 times 10 raised to power 2 Newton, and this is the solution. Now the work done is force F cos theta times S, that is the force times cos of the angle theta times the displacement. And from our question, we can see that the force is 1.20 times 10 raised to power 2 Newton, and the theta is 30 degrees, and the S is 5. When we do our multiplication, we get 5.2 times 10 raised to power 2 joules. Now, work done in a force field. An example of a force field is the Earth's gravitational field. In the gravitational field, there is always a force pulling a body towards the center of the Earth. We must have known about fields. There's what we call gravitational field that tends to drag bodies towards the center of the Earth. That is why when I throw this pen up, it is bound to come down because of the work done on it by gravity. Now, work done in a force field can be explained in two ways. We have lifting a body and falling bodies. We can see that this man here is lifting a load. This load initially was at the bottom. Now this man has succeeded in lifting this load. The work is done from this. Work is done as he lifts this body up to this distance. Also, this fruit from this tree falls to the ground as a result of gravity, and that is work done. Now let's consider the first case, lifting a body. Now to lift a load through a height, h, a pulling force must be applied to overcome the weight of the body, which acts downwards. Now you must know that the weight of a body always acts downwards. So to lift a load up, you must work against the force of gravity, and that is work done against gravity in lifting that load upwards. Therefore, when an object is lifted vertically upwards, work is done against the force of gravity or against the weight of the body. So that is to say that for you to lift a body up, work has to be done for you to overcome the force of gravity. The magnitude of the work done is given by work is equal to force times distance, as we earlier stated. But we should also know that force is mass times acceleration due to gravity. Hence, work is equal to mass times acceleration due to gravity times height. Work is equal to mgh. Now, you can relate this to this equation of force times distance. We all know that force is mass times gravity. And in this case, this distance is a vertical distance of height, which is h. Because when we talk of gravity, we talk about vertical displacements. So that is why we use height. Like the case of this boy, this is the height. He's trying to move upwards. Now let's see an example. A boy of mass 50 grams ascends a flight of stairs of vertical height 250 centimeters. Find the work done against gravity. Now you can see from our question, remember I said we work with the SI units. So we need to make some conversions. First, the 50,000 is in gram and the height is in centimeters. And remember the SI unit for mass is the kilogram and the SI unit for length is the meters. So we need to convert 50,000 grams to kilogram. That's 50,000 grams is equal to 50 kilograms because we know that 1,000 grams is equal to 1 kilogram. So 50,000 grams will be equal to X. So X is equal to 50,000, when you cross multiply, divided by 1,000. Which is equal to 50 kilogram. So we have succeeded in converting the mass in grams to kilogram. Now let's look at the heights, which is in centimeter. We have 250 centimeter. We are converting it to meter. And we know that 100 centimeters is equal to 1 meter. Therefore, 250 centimeter will be equal to x. So x is equal to 250 divided by 100, which is equal to 2.5 meters. So we have also succeeded in converting the 250 centimeters to 2.5 meters. Now let's calculate the work done. Now the work done, remember, it is force times distance. But also remember that force is equal to mg. Then work done will be equal to ngh. So it's equal to 50 kilogram times 9.81 meters per second square times 2.5 meters. Remember, your acceleration due to gravity is a constant, which is 9.81 meters per second square. This is a constant that you must all know, that the acceleration due to gravity is 9.81 meters per second square. So when you multiply out, you get 1,226.25 joules. Then now the second category, which is falling bodies. The Earth's gravitational force does work on bodies. Now, for a body to fall, it means the work done is actually by gravity. The other one, to lift a body, the work done is against gravity. But for falling bodies, the work done is by gravity. So when a body falls freely in a force field, the force of the field does work on the body. Consider a body of mass m falling through a vertical height. The work done by gravity on the body is given by mgh, where m is the mass of the body, g is the acceleration due to gravity, and h is the vertical height. Let's take a look at this example. A ball of mass 6 kilograms falls from rest. Now this is a work done by gravity because it falls from rest from a certain height of 450 meters. Calculate the work done by gravity on the ball. And from the question, we can see that our mass is 6 kilograms, our height is 450 meters. Then the solution, work done, remember, it is mass times acceleration due to gravity times height. And our mass is 6 kilograms. Acceleration due to gravity is 9.81 meters per second square, and our height is 450 meters. When you multiply out, you get 26,487 joules. This is a very simple question. Now, let's take a look at the nature of work done. Now, work done can be positive, it can be negative, and it can also be zero. I'm going to look at the conditions. What makes work done to be positive? What makes work done to be negative? And what also makes work done to be zero? Now, let's look at positive work. Work done by a force is positive when the force and the displacement are in the same direction. You must take note of this word, same direction. When the force, for the work done to be positive, the force and the displacement, remember that the two parameters involved in work done, force and displacement. So for work done to be positive, the force and the displacement must be in the same direction. That is, the force is parallel to the displacement. If the force is acting along the horizontal path, what do we mean? Take a look at this picture here. The force applied to this body moves the body to point B. Now, the force applied is in this direction. You can say it is in the positive x-axis. And the displacement is also in this direction, in the positive x-axis. If I'm to calculate the work done on this by this force, it would be positive because the force and the displacement are in the same direction. The second one is the force acts at an angle to the horizontal in the same direction to the displacement. That is, the force acts at an angle. Now, it's no more parallel. It's now acts at an angle to the displacement. That is, the angle between the force and the displacement is an acute angle. And we all know what acute angle is. An acute angle is an angle between 0 and 90 degrees. It is greater than 0 and less than 90 degrees. Any angle greater than 0 and less than 90 degrees is an acute angle. For the work done to be positive, the angle between the force and the displacement must be an acute angle. Take a look at this diagram. This is the initial position of the body. It was displaced to this position, and this is angle theta. The force is at an angle theta to the horizontal. So such a case, the work done is positive. Now, negative. When can we say this work is negative? Work done by a force is negative when the force and the displacement are in the opposite direction, but on the same axis. You must take note of these words. For the work done by a force to be negative, 1, the force and the displacement must be in the opposite direction, but on the same axis. We know our Cartesian plane. We know this is y-axis and this is x-axis. And we know when we talk about work done, we are mainly concerned with the horizontal direction. So it means that if the force is applied this way and the displacement is in this direction, the work done will be negative. That is, the force is opposite the displacement. Like the case of this diagram, you can see that the force is in this direction and the displacement is in this direction. In this case, the work done will be negative. Now, the force acts at an angle to the horizontal in the opposite direction to the displacement. That is, the angle between the force and the displacement is an obtuse angle. What is an obtuse angle? An obtuse angle is an angle between 90 degrees and 180 degrees. That means it is greater than 90 degrees, but less than 180 degrees. So any range of angle that falls between 90 and 180, the work done will be negative. We can see, for instance, this is a sign of an obtuse angle. We can see that the force is in this direction and the displacement is in an opposite direction, but in the same axis, in the horizontal axis. Now, when is the work done 0? Work done by a force is 0 if the force is perpendicular to the displacement. That is, the angle between the force and the displacement is 90 degrees. When we talk about perpendicular, we talk about something like this. When it's at 90 degrees, we say it is perpendicular. So when the force is perpendicular to the displacement, we say that the work done by the force is 0 because cos 90 is actually 0. Now, the second condition is there is no displacement. That is, the displacement is equal to 0. For instance, if you try pushing a wall, after applying so much force and effort to that wall, if it does not move, if the wall does not move, it means that the displacement is 0. And if the displacement is 0, automatically you have not done any work. So if the work, for a work done to be 0, it means the body was not displaced. The body did not move. Take a look at these diagrams. This rock, after applying so much force, the rock did not move. Neither did this heavy stone nor this drawer. None of them moved after so much force has been applied. So when you apply force to a body and the body does not move, no work is done. The third condition is there is no force acting on the body. That is, the force is equal to 0. When there is no force, when there is no push, when there is no pull, then the work done is 0. Remember our definition of work done. Number 1, force must be applied, the body must be moved, and it must be in the direction of the force. Now we have come to the end of this lesson, but let's refresh our minds on what we have learned so far. Work is said to be done when a force F moves a body through a distance S in the direction of the force. Hope you remember we talked about work. Work is also the product of force times displacement. Work is measured in joules. We have different nature of work. Work can be positive, work can be negative, work can also be 0. We also talked about work done against gravity in lifting bodies and work done by gravity in falling bodies. Now let's take a look at this test question. A body of mass 5 kg is placed at the origin and can only move on the x-axis. A force of 10 Newton is acting on it in a direction making an angle 60 degrees with the x-axis and displaces it along the x-axis by 4 meters. Calculate the work done by the force. A, you have 10 joules, B, 20 joules, C, 100 joules, and D, 200 joules. Now you can see from this question, the data given, we have mass. Mass is equal to 5 kg. And we are told that this mass is placed at the origin and can move on the x-axis, which is the horizontal direction. A force of 10 Newton is applied. Now we can sketch this diagram. This is your Cartesian plane. This is the origin, as we all know. And there's a body at the origin and can only move and can only move on the x-axis, and this is the x-axis. A force of 10 Newton is acting on it, making an angle 60 degrees. A force is acting on it, making an angle 60 degrees with the x-axis. And it displaces the x-axis by 4 meters. That is 4 meters. Calculate the work done by the force. Now this is the sketch, this is the force, and this is your displacement, which is S. Now you can see that this work has been made easier through the sketch. Now the force, which is your data given, is 10 Newton, and the angle theta is 60 degrees, and your displacement is 4 meters. So work done is equal to force, which is F, cos theta times S. So your force is 10 times cos 60 times 4. 10 times your cos 60 is 0.5 and times 4, which is equal to 10 times 0.5 is 5. 5 times 4 is 20 joules. So your answer is B. I hope you got that right. The second test question is, what is the net work done when a box of mass 10 kg is pulled on a horizontal plane of length 5 meters by a force of 80 Newton? Then it is raised vertically to a height of 10 meters. And your G, which is your acceleration due to gravity, is 9.81 meter per second square. A, 981 joules. B, 1,381 joules. C, 400 joules. And D, 1,400 joules. Let's take a look at the solution. We were asked to calculate the net work done. That is the total work done. When a box of mass, you have mass to be 10 kg, is pulled on a horizontal plane of length, that means your S, which is your displacement, is 5 meters, by a force F of 80 Newton. then it is raised vertically to a height of 10 meters. And our g, which is acceleration due to gravity, is a constant, which is 9.81 meters per second square. Now, what is the net work done? First, we know that work done is equal to force times distance. When you're talking about, or displacement, when you're talking about horizontal direction, it means the work done was the work done by the force is F times S. And we know that the force is 80 Newton and the displacement is 5. So we simply have 80 times 5, which is 400 joules. But remember, we're asked the net work done. So this is work done 1. So work done 2, the second work done, said the body was raised vertically. So there was a work done against gravity, which is mgh. So we have mass to be 10 times the acceleration due to gravity, which is 9.81, times height, which is 10. When we multiply, we have 981 joules. So the total work done is equal to the first work done, which is WD1, plus the second work done, which is WD2, which is equal to 400 joules plus 981 joules, which is equal to 1,381 joules, which is B, option B. I hope you learned a lot from today's class. I hope you can remember what work is, the unit of work, the measurement of work, work done against gravity, work done by gravity, the nature of work, when work is said to be positive, negative, or zero. And I hope to see you again in the next class. Bye.